Sorry about that. Yeah, sure. Oh, perfect. Forward and backward. Okay. So there's somebody. Oh, okay. Let's give it a try. Yep. Yep, perfect. Thanks.
Okay, welcome everyone. We are very happy to have Oren Louidor from Technion, and today he's going to talk about the limit law for the most favorite point, the simple random walk on a regular tree.
Okay. So thank you very much for the invitation. It's a pleasure to be in India and in this conference in particular. And I'm going to talk about joint work with Marek Piskov, who's been my co-author for many years now. And I apologize, I know there's at least one person in this room who have seen this talk already. Okay. So, so what is this talk about? It's a very simple model. So you take the rooted D RE tree. You can think of the binary tree for the rest of the talk. Okay, I'll denote the leaves by LN and the root by rho. Here. And then you run a continuous time simple random walk, by which I mean that at every vertex, so when the walk is at a given vertex, you run, or it runs exponential clocks with rate 1 on each of the edges emanating from that vertex. And when the first edge rings, it jumps to the neighbor, to the corresponding neighbor. Okay, and I'll denote by PZ the law of this walk starting from Z. Okay, and I'll be interested in the local time. So this is okay, it's kind of discrete state space, so it's easy to define the local time. And for me, the local time would be so the local time. So this lowercase l t of x would be the local time of the time spent by the walk at vertex x until time t, okay, until the walk is run by time t. And the question that, okay, I'll talk about the history slightly later, but the question that somehow interested people dating back many years ago is what is the local, what is the behavior, what is the probabilistic behavior, asymptotic probabilistic behavior of the maximal local time from among all the leaves. And so that's the question. And so let me start with the answer. Okay, so of course this answer will depend on where you start. Well, might depend on where you start from. Okay. Okay, so and when you end, of course. So I'll show a different. So I'll have various results for different, okay, kind of slightly different setups, so starting points and ending conditions. But somehow maybe the most canonical one, and I'll explain why it's canonical later, is that you start from one of the leaves, and then you run the walk until the first time it hits the root. Okay, so notice if you think about the height of the walk on this binary tree, in this BRE tree, the height of the walk is is kind of a random walk by itself, and this random walk has a drift towards the leaves. And so it will take the walk quite some time, exponential time, to get back to the root. Okay, so it's kind of meaningful. And the question is, okay, what is the how does the maximum behave? And here's the here's the answer. Okay, so it turns out that if you so if you take the maximal, okay, we call this the most favorite point. So the point where the maximum is attained is the most favorite point, and there'll be time at the most favorite point. So the local time at the most favorite point, if you take the square root and you subtract, okay, so in first order you subtract, it's a linear, and second order is logarithmic, and if you subtract this, then you get convergence. And what do you converge to? Well, you converge to a Gumbel distribution, okay, shifted by this independent random variable S, who's from, okay, for the moment I'm not saying it, okay, on which I'm not saying anything for the moment. Okay, I'll say what it is in the next slide. Okay, so equivalently, if you want a more without square roots, so okay, so if you look at the maximum itself, then the first order is n squared, the second order is n log n, and then whatever remains is our fluctuations of order, of linear order. Okay, and if you divide by that, so that's kind of that's kind of a more standard formulation for scaling limit. I should say that this connects, of course, to previous talks that we've seen in this conference, in particular Ofer's talk. So Ofer was talking about logarithmically correlated fields, and one of the features, or one of the universal features of logarithmically correlated fields, was this emergence of this randomly shifted Gumbel as the limit law of the maximum. And indeed, this is, so if you look at the square root of the local time, square root of the local time, that is indeed approximately logarithmically or hierarchically, because it's a tree, logarithmically correlated field. And I will say something about it in a few slides. Let me remind you that Ofer was talking. Okay, Ofer was talking about branching Brownian motion, which is a closed sorry, Ofer was talking about the local time on various other graphs, and he was also mentioning the cover time. So this is kind of the opposite. So here we are interested in the point where the local time is maximum. The cover time, you're interested in at the point where the local time is minimum. You want to know what's the time, how much time do I have to run the walk until the minimal point is already positive. So it's kind of the opposite side of the spectrum. Okay, so let me look at a slightly, it turns out that in order to solve this problem, at least in the method of proof that we propose, it's easier to first look at a slightly different setup. Sorry, but before that, I forgot to say something about S. So what is this S? Okay, there is a description of S. It's okay, it's a description. It's not okay, it's not very explicit. So here it is. You take this creature. Okay, so it's you sum over the leaves and you sum this particular function of the or functional of the local time field on the leaves. I'll try to give some insight for where this comes from in the end, towards the end of the talk. For people who are familiar with logarithmically correlated fields, or in particular the branching random walk, this is somehow reminiscent of the derivative martingale that Ofer was also mentioning. Okay, and then it turns out that this random creature has a limit in law as n tends to infinity, and this limit in law, if you take the log of this guy and you normalize it properly, then this is S. Okay? And turns out that this, okay, and you can prove that this, okay, this logarithm, okay, this is a proper random variable. Okay, in that sense. Okay, so that's S. Okay, so now, as I said before, instead of looking at the original problem, let me look at a slightly different problem. So instead of starting at a leaf and waiting until the walk reaches the root, let me start at the root and wait a prescribed time. Now, this is not going to be the running time of the walk, but rather I'm going to wait until the time at the root is t. So this is kind of like the generalized inverse, sorry, of the local time at the root. So I'm waiting until okay, so I'm running the walk until until the walk has accumulated t time at the root. Then I stop, and now I ask, okay, what is the maximal local time? And for ease of notation, let me denote by LT of x the local time at x when I've stopped this process. So when the local time at the root is t. Okay, so it will be capital T of x, and it turns out that the reason that we do this is that it's an easier process. This LT of x is an easier process to work with than this little T of x, and I'll show this later. It turns out, okay, this is infinitely divisible, for instance. Okay, so here's the theorem. Okay, so what if you do that? If you look at the maximal local time in this setup, so now things, of course, will depend on t, because it really depends on how long you run the walk for. Okay, and here's what you get. So notice that it's quite similar to what you got before. So before we got these two terms, and now there's this additional expression that depends on t. Okay, and the convergence is still to the same gumble, but now the shift is slightly different. Turns out that the shift depends on t. And another feature that was not apparent, was not there before. So before the maximal local time, okay, is always okay. It's somehow always growing in this at this rate. Here, if I start from the root and I wait t time, there is a possibility that I've never reached the leaves. For instance, the exponential clock at the root never rang. So that means that, okay, and that's something that will happen regardless, uniformly in n. So there is a positive probability that that this limit, okay, so if there is a weak limit for this, then this limit would have an atom at negative infinity. Because if this is 0, then this will go to negative infinity. So indeed, this S of t is a random variable that has an atom at negative infinity. Okay. And so it's not a proper, in that sense, it's not a proper random variable. And here's the, okay, and here's the, okay, and here's how you get S of t. So it's kind of similar to before. It's okay, slightly more convoluted. So that's the expression. And indeed, so again, you start from this random creature. And then it turns out this random creature has a weak limit. And the log of this limit is your random shift. And as I mentioned before, this can have an atom at negative infinity. And the probability that it has this atom is exactly the probability that you never reach the leaves. Okay. Okay. So what's the connection between between z of t and z? So the shift in this problem versus the shift in the previous in the original setup. Well, the difference. Okay, what's the relation? So the relation is given by this formula. So if you take this zt, you condition it to be non-zero, and you take t to 0, then in law this z of t will converge to z. So z of so z of z is the limit of z of t as t tends to 0, but under the conditioning that it's not 0. And the way to see why these two problems are related, starting from the leaves and starting from the root, is the following. So if you start from the root and you wait t units of time, so okay, there is a chance that of course you did not reach the leaves, and then nothing happened. But if you did reach the leaves, then and that happens with positive probability regardless of n, because the height of this walk is indeed a biased random walk. So if you did reach the leaves, then well, until you reach the leaves, you did not accumulate any local time at the leaves. Once you've reached the leaves, now okay, you've reached a randomly uniformly chosen leaf, and now it's as if you started from the leaves from that particular leaf, and so now we're in the domain of the original, or in the original setup where you start from the leaf and wait until you get to the root. Okay? So condition on reaching the leaves, we arrive to the, so if you start from the root and you condition on reaching the leaves, then you arrive to the setup of starting from the leaves. Okay, but in the original setup, you stop the process when you reach the root. Here, okay, you don't stop the process when you reach the root. You stop the process when you accumulated t time at the root. And so in order to make sure that you don't, okay, so in principle, not just in principle, there is a chance that you'll make another excursion to the leaves and do another kind of accumulation of local time until you reach the root and so on. So in order to make sure that this doesn't happen, what you do is you take t to 0. So okay. Okay, you can prove it's okay. So that's kind of manifested here, but you can prove that if you look at the maximum in this setup, and you condition on reaching the leaves, and so you condition on reaching the leaves, and you take t to 0 to make sure that after you reach the leaves you don't make another excursion. Then the maximum, the law of the maximum becomes is uniformly close to the law of the maximum of the setup where you actually start from the leaves. That explains this. Okay, so okay, let me now give you a seemingly completely different problem, extreme value problem, which is the well-known by now classical problem of the maximum of a branching random walk. Okay, so what is a branching random walk? Let me remind you. So, okay, so this will be a branching random walk with Gaussian steps and binary deterministic branching. Okay, but okay, maybe simpler terms. Apologize. So you take your tree, Tn, and you put, okay, I need this normalization. So you put Gaussian, centered Gaussian random variables with variance 1/2 independently on all the edges. And then, okay, then you define a field h of x, and the value at x is just the sum of these Gaussians on the edges leading from the root to x. Okay, so that's a standard branching random walk. You can think about it as a particle that branches to be child particles, and each of them makes a displacement relative to where the parent particle was of that magnitude. And then if you look at the collection of displacements of all particles, and you call this h, then this becomes exactly this h. Okay, so this is called the branching random walk, and it's also called the discrete Gaussian free field on Tn with 0 boundary conditions at the root. And you can easily compute, okay, so it's clearly a Gaussian process, and you can easily compute the covariance structure. It's centered in the covariance structure. So if you have two vertices, you just look at the common path. So the common part of their path of the path to x and the path to y from the root, and the size of that path, or the length of that common part divided by 2, that would be the covariance. Okay. And now you introduce, okay, so we have this Gaussian. Okay, so we have this multivariate Gaussian, and now you introduce, okay, another random creature, which this time I call Wn, and it's kind of somehow reminiscent of this Zn that I had before. And again, okay, now for people in this field of branching random walk, this is honestly an honest, this is called, in fact, the derivative martingale for that branching random walk. And turns out, okay, so that's called the derivative martingale because it's indeed a martingale. It's also a derivative of some other martingale. That's why it's called the derivative martingale. And you can prove, okay, it's not a positive martingale, so you don't necessarily, okay, so there are no martingale theorems that guarantee that there's a limit, but indeed there is you can show that there's a limit, and this limit is, okay, is non-trivial. Okay. So I'll call this limit W, and then, okay, and then it turns out, somehow for the moment, it's not so clear why, that if you look at the maximum of this branching random walk, in the language of particles, you can look at the right, okay, the top particle, the particle that went the furthest away, and you subtract a quantity that looks somehow similar to the quantity that we had before we had this, but the normalization here was 1 over, it was 1, not 3/4. Okay, but in any case, if you do that, then you converge to again something that looks very similar to what we had before. It's again the same Gumbel with the same rate, but now R is a different shift, so there's a different random shift, and the random shift is related to this W from the previous slide, like this. So then, well, okay, so then they all seem kind of similar. So is there any connection between them? Okay, so I'll say, okay, so first of all, okay, you can show, and that will be maybe explained in the next slide, that that if you take this Z of T, the shift in the second setup, random, not the shift, but the exponential of the shift, in the second setup where I run the walk until T time at the root, and you take T to infinity, then in fact you get this exactly this W here. So somehow the kind of funky derivative martingale that we had here and the real derivative martingale, or the real derivative martingale is the limit in law. So why are these things related? So why is the branching random walk and the local time and the maximal and the local time related? And that's actually a very simple. So in Ofer's talk, we have already saw a connection between the branching random walk or so the Gaussian free field, discrete Gaussian free field to the local time via the so-called isomorphism theorem. Okay, so there is a formula that relates in the law of the Gaussian free field, or branching random walk in this case, and the local time field. But we don't need this. So okay, the formula is okay. The fact that it's precise okay, is very helpful. But okay, in many cases, but we don't need such a fancy tool here. In fact, all we need is the central limit theorem. Okay. Why is the maximum or why is the branching random walk and the local time related? Well, okay. So the fact. So notice, as I mentioned before, and that's kind of the advantage of this parameterization is that if I look at the random walk until I spend t time at the root. Well, then I can, okay, then it's infinitely, okay, this whole field is the whole local time field is infinitely divisible. I can, for instance, I can, okay, I can add k independent copies of this field, where each time I just wait until I spend 1 unit of time, or sorry, t over k units of time at the root. It's easy to see because of okay the Poissonian structure of the jumps. Okay, and okay, so that means that this local time field is okay is a sum of independent identically distributed random variables. So there should be a CLT. So CLT is in force. So let me write the CLT like this. So the local time after t units of time. So think about it as if I'm okay, I'm adding t instances of the local time field in which each time I run the walk until 1 unit of time at the root. Okay, so altogether, what do you have? So you'll get a Gaussian with the right mean and the right variance. So what is the mean? The mean is just okay t times the local time if I run the walk for 1 unit of time, and the variance okay would be t times the covariance if I run the walk for 1 unit of time. And if you do this computation, then okay, then the local time at okay, the local time indexed by x is actually a martingale. So the local time, okay, it's not difficult to see. The local time at any vertex will be t. So it will be 1. Sorry, if you run it, or t if you run it for t units of time. And then it's not difficult to see that okay, it's very easy. It's the tree here. So the covariance between local times at x and local time at y is just twice times the joint part of the path from the root to x and y. And lo and behold, this is really okay. This looks almost like the law of the Gaussian free field. In fact, if you take the square root of the local time, okay, so you take the square root of that, then by Taylor expansion, you get on first order you'll get square root of t, and then the second order you get this divided by 2 square root of t, and okay, and if you and then okay, so then you can see that asymptotically, when t tends to infinity, up to little over 1 corrections in probability, you get okay. If you take the square root of the local time, you subtract square root of t, you get a multivariate Gaussian with this covariance. But that's exactly the branching random walk or the Gaussian free field. Okay, so the branching random walk is the kind of scaling or the scaling limit of the local time, or okay. Okay, so that kind of explains why local time and branching random walk are related. And okay, in fact, you can okay. Another way to see this is to okay. One way to use this is to actually okay. So somehow look at whether you can simultaneously see the convergence of the branching random walk and the local time okay, at the same time, the local time field at the same time. Okay, and that leads me to this uniform tightness result. So let me actually present it first. So Okay, so there is kind of a, you can show, okay, what I'm going to show is a kind of how do you transition from the local time to the limit, which is this branching random walk. So it turns out that, okay, if you want a unifying centering sequence, this is kind of the unifying centering sequence. So for the Gaussian free field, we had this centering, and for the branching random walk, so we had this centering sequence, and for the local time we had something else. And somehow to kind of see them both at the same time, okay, you introduce this object. I should say that this object is due to Abe, who studied the maximal local time on the branching random walk, but at the time scales which are much higher. And I'll say something about it later. Okay, so here's the result. The result is that if you look at the okay, so if you look at the maximal local time, then then it's tight around square root of t plus this centering sequence, and that's true simultaneously for all n and all t. Okay, and why am I saying that this is kind of showing both the branching random walk and the maximal local time at the same kind of at the same time, or capturing both simultaneously? Well, okay, so if you look at this centering sequence, and if you fix n, okay, if you look at this centering sequence, and if you fix n and send t to infinity, so when you send t to infinity, this will disappear. Okay, and so then you're centering by, okay, so then you have this centered by this, but as t tends to infinity, we have seen that this converges to the branching random walk or Gaussian free field. So, okay, so for fixed n, if you first take t to infinity, you get the branching random walk here centered around the centering sequence for the maximum. So that kind of captures this. And on the other hand, if you fix t and you don't send it to infinity, but you rather send n to, okay, you just send n to infinity, then then this square root of t somehow, okay, when t is fixed and you send t to infinity, this is immaterial, and you get, okay, this gives you 1/4 log b log n, that kind of joins with this, and you get the 1/square root of log b, sorry, 1/square root of log b times log n. That was the centering for the, that was the initial centering for the local time problem. And then you get this square root of t multiplied by this. So you get, okay, you have also the square root of t here. So you get altogether this. But in other words, what you get is really the centering sequence that I've shown you before for the local time. So that's kind of how you see both of them together. Okay. And okay, so I want to tell you briefly about, first I want to tell you a little bit about the history, and then I'll give you this kind of a snippet from the proof. Okay, so the real, I should say this is a toy problem. The real interesting problem is not the tree, of course, but rather the box. And it turns out that, and this was also somehow mentioned in Ofer's talk, that the relevant dimension is 2. So somehow random walk in, okay, so the green function in two-dimensional planar domains, and the green function on the random walks on trees and random walks on two-dimensional domains behave in many ways very similar. These two geometries are entirely different. Okay, so the real problem was posed, well, more than 60 years ago by Erdos and Taylor. Problem on the box is that you start, instead of a leaf, you start from the bulk of a two-dimensional box, n by n, and you run, instead of running the walk until you reach the root, you run the walk until you reach the boundary of the box, and you want to know what's the maximal local time. Okay, so typical number of times that you spend at the vertex is log n. Before, if you visit the vertex, okay, you spend log n time at a given vertex. That's just the inverse of the green function. But then, okay, question is what is the value, what is the largest time spent at a given vertex? And they were able to prove these two bounds, 1/4, okay, so a lower bound of 1/4 pi and 1/pi as an upper bound, almost surely, I mean. So that, I mean, you can do all of this in the same, you can realize all of them on the same probability space. Okay, so I should say that our problem is just a toy case, or kind of a toy way to do this. On the tree, you start from the leaf instead of the bulk, and you end until you get to the root. Okay, and then in the seminal paper of O1 that again Ofer mentioned, they will, so these four were able to show that 1/pi is indeed the limit on first order, the leading order asymptotics, so log n squared times 1/pi. You should think of n, okay, I should say the connection between what the result that we have and this result. So our little n, you should think of it, think of capital N as 2 to the n, is 2 to the n, or log capital N is little n. Okay, so here the leading asymptotics is, so you can think of the box as having size 2 to the little n. Okay, so this is just amounts to n squared. Okay, which is the same asymptotics that you get to in the same qualitatively the same asymptotics as you get in the tree. Okay. Okay. And I think the most, I mean, there have been also developments after, but the most kind of state of the art for the moment is a paper by J. Rosen that shows okay, that the following is the right, okay, that the following sequence is tight, so there's still no weak convergence. Again, you should think of it as this as little n, and this is, so this is log n, and it's exactly linear minus logarithmic. It's the same asymptotics as in the tree. Okay, and okay, and J. Rosen proved it not for a random walk, but rather, okay, there is some analogous model using Brownian motion. So instead of looking at the most favorite point, you look at the occupation measure inside each point in the unit box, and you wait until, and you look at at points where the kind of the rate of decay of the size of the occupation measure decreases, you know, slowly and the slowest. Okay, but there is kind of a kind of a natural analog in the case of Brownian motion, which was also used to prove that. So they first proved it for branching for Brownian motion and then converted it to random walk. Okay, I should say that there is, although there is no proof for weak convergence, there is a candidate for the limiting law of the maximum, and that's given by the total mass. Okay, so that's given by a Gumbel shifted by the total. So it's conjectured that, of course, that the limit. Okay, maybe I should have said that. So it's conjectured that the weak limit of that this converges to, or in the even the random walk setting, this converges to a randomly shifted Gumbel. And the question is, okay, and the shift. So what is the shift? The shift would be the total mass of this of a random measure, which is called critical Brownian multiplicative chaos. I'm not going to get into this. It's an object that was introduced by, well, not okay. So by a few people independently. One of them was Hugo in this context in 2020. It encodes more than just the maximum, but also the second maximum and third maximum and so on. So that is the kind of the candidate, but there's no proof that this is indeed the limit. And I should also mention what I mentioned also before is that Abe, so when our paper uses some of the results in that paper, so Abe has proved a convergence in law again for the maximum on the tree. So everything is the same as as in our case, except that the time scales are much larger. So you have so he looks at the case where you start from the root and wait t units of time, and then these t units of time cannot be of order of order 1, they have to go and at least like n log n. And so really, so there's quite a bit of difficulty in getting these two t's, which are of order 1. And in particular, that's required if you want to start from the leaves. In particular, you always recover here the derivative martingale because t is always tending to infinity. So you always recover the usual derivative martingale and not this funky derivative martingale z that we have. Okay, so in the remaining minutes that I have, I want to give you some insight of the proof. I'm not sure that this is the best part of the proof. I should have maybe chosen a better, but it's okay. Okay, the proof is kind of lengthy, so okay. So in any case, I need to show you a specific part of it. Okay, so I'm going to show you how to. Okay, I'll give you some ideas about how to prove theorem 3. Theorem 3 is the theorem where you start from the root. I don't know if I'm writing it here. So here's, let me actually show you theorem 3 first. So theorem 3 is this. So if you look at the maximum, take the square root, subtract the centering sequence, that converges to this randomly shifted Gumbel. So that's what I'm trying to convince you. Okay, so as in other works in the subject of logarithmically correlated fields, one way of proving weak convergence is by first deriving not weak convergence, but sharp uniform asymptotics for the upper tail of the maximum. So if you want, in other words, if you want to prove asymptotics for the probability that the maximum is after centering is bigger than t, first thing you want to do is derive asymptotics when t tends to infinity. Okay? For this quantity, and so okay, so this is some notation. So this is just the CDF of the maximum, and this is with the hat. That will be the CDF of again, the square root, sorry, of the maximum. This is the centered CDF. So this is the centering sequence, and I'm using this AN of t that I wrote before. So okay, this is just okay, this shift of that. And as I mentioned, well, the first thing you want to do is you derive asymptotics when t tends to infinity. Okay, and here we'll take asymptotics both when t and u. Sorry, I said t. I meant before u. So you take asymptotics. You look at the right at the upper tail. So you take asymptotics of u when u tends to infinity. But in our case, it will also be convenient to take t to infinity. T is the time spent at the root. Okay, so here's okay, and okay, so here's the sharp tail asymptotics. So the tail of the maximum has this kind of exponential times a linear factor. And that's again kind of reminiscent in all of the logarithmic, another signature of logarithmically correlated fields. Okay, so that's kind of so this is so that's that's kind of a first step in many of the derivations in this business. I should say that one of the reasons that you do this is that as you can see, there's no additional okay, so kind of randomness like we had in the real asymptotics, not just for the tail, where okay, where you have kind of a randomly shifted Gumbel. Here it's okay. There's a constant. Okay. So I'm not going to show you how you derive this, but I'm just going to show you how you use this sharp tail asymptotics to actually derive the weak convergence. I should say that an upper bound of this sort was proven by Abe, and he proved it for his purposes, where T was okay. And we in fact can just take it from him, from his work. The lower bound is okay. So Abe has a lower bound, but it's not okay. But it's not precise as that, and so you have to work to get this precisely. Okay, but once you have it, there is kind of a standard way, and that's what I'm going to show you how to get the weak convergence. Okay, so that's what I said. It's kind of a standard step. Okay, so okay, so what do you do? So I'm going to condition. Okay, so I want to know the probability that want to find asymptotics for the probability that the maximum of the square root of the local time in n generations after centering stays below u. Okay, so what I'm going to do is I'm going to condition on the first k generations, and I'm going to restrict. Okay, so I just copied. This is the tail asymptotics that I have. Okay. And I'm just I'm going to restrict all the positions or all the particles, the particle interpretation at generation k to be below this, and that's okay, and that's that's an event that happens with probability or with high probability, with probability tending to 1, because we know that by this tail estimate we know or by the tail estimate we know that that this stays below. This is the right centering sequence, right? So this in particular tells you that this is the right centering sequence. And so I can freely add, okay, so I can freely add this event. Okay, so I'm adding this event, and I'm only paying order 1. And once I add, okay, so I'm adding this event, and okay, so the probability, let me write this. So the probability, the centered probability, CDF is the original CDF with this centering. I'm conditioning on generation k by the branching structure, Markov structure. It just amounts to all of the children. So the probability that I'm staying below that is the probability that all the children stay below that. If I look at the remaining n minus k generations, and I start, so for a particle x at generation k, I start from the local time, from his local time at generation k. That's another advantage of looking at this LT, that it has this nice Markovian structure, this capital LT. Okay, so that's just a recursive relation for the maximum. And now I'm going to replace this back to the centering, to the centered version. So I just added the centering. And now what I want to show is that with high probability, if you restrict to this event, you are the so-called in the tail. So this is going to tend to infinity. So you're in the tail, and if you're in the tail, we can use this formula. Okay. So, oops. Okay. So let me call this thing inside. Let me call this. Let me give the name. Let me call it U. It's just this rearranging terms. Okay. And so this is U. And okay. And then you can do you should just do the computation modulo some technical details. Okay. So if this is less than square root of, if this is less than AK of T, okay. So you just plug this in here. And then you estimate these three, this expression, and turns out that indeed this expression on the event AK is going to infinity. Okay, and it's not difficult to see. I mean, on first order, these are all linear. So this is linear in n, and this is n minus k, and this is k. So the linear part gets cancelled. Then you have a logarithmic part, but by the concavity of the logarithmic function, you get a surplus here. This surplus is log k, and and this doesn't beat it. Okay, you need to slightly work harder because an has other terms, but okay, that's not so much of a problem. And then this grows. So you are indeed you are in the tail. So you can use the asymptotics, and moreover, you can show. And I'm kind of lying just a little bit here, and you can show that in fact. Remember that I'm fixing T and I'm fixing U in this derivation. So when you take k to infinity, you can actually, so if you go back to this, okay, this essentially on first order gives you a linear term in k, this k, okay, t is fixed, u is fixed, and so, okay, asymptotically, you just get the linear term here minus the square root. Okay, I'm lying just a little bit, but okay, but it's not so bad. Okay, and then you just plug this back in. So, okay, so so I'm going to, now that I know that I'm in the tail here, I can use this formula and I plug it in here. I do some, okay, so let me just do this quickly. Okay, so so this is plugging in, okay, so this is just u. I'm just plugging in this, okay, just plugging u, and then I'm replacing u by, okay, outside by this formula and inside by the full formula. Okay, so that's that. Okay, let me not go through this too carefully. And okay, and then okay, and then you get, okay, after some massage, you get this, and now you notice that, oh, maybe you can recognize now that this from this point to that point is precisely the zkt that I had before. Okay, so you can write it kind of economically in this way, but now you have okay, two terms, two sequences, one that depends only on n, the other one that depends only on k, and they become arbitrarily close to each other as n and k tend to infinity. Well, that must imply that this has a limit and this has a limit. This can be seen as the okay, this is the Laplace, can be seen as the Laplace transform of this zk, and so if the Laplace transform of zkt has a limit, this limit must be, so it must have a weak limit. And so as a conclusion, you have that this zk of t converges to a limit. And okay, and then you can plug it in. So you plug this in, and again, part of the conclusion is that this converges to a limit. And so you get that the limit of this is that. But then this is really precisely saying that the CDF of the centered maximum is a randomly shifted Gumbel. Okay, so this is the Gumbel, and this is the random shift. You can see it. You can see it here. So I guess this is all I wanted to say. Maybe except that we're looking for postdocs. So if you if you have you're a postdoc or you know of postdocs that are interested in doing a postdoc in Technion, let me know. I'll stop here.
Thanks, Soren, for a wonderful talk. Now time for some questions. Okay, yeah, so I'll ask a few questions. So this expression ZNT, is it a martingale or
no? Well,
it is not.
I don't think it's a martingale. No.
Okay, and similarly for ZN, where North Star from.
No, I don't think it's a martingale, but we didn't check. Okay. But I don't think it's a martingale.
Okay, and instead of like a regular tree, if you do a similar thing on, say, a Galton-Watson tree, then do you think the results will go through?
Probably, yes. I mean, there are analogs of this derivative martingale. So of course, for branching which are not deterministic. Yeah, I don't see a problem. You need, of course, to have it supercritical.
Mm-hmm. Yeah, and so like for the expressions LTX, see, if I consider a process which has the same marginals but has correlation 0.
So which
like before, if you go behind where you had the correlations kind of similar to the after scaling, you had similar correlations to branching dynamic. Right.
Maybe here.
Yeah.
Oops.
Right. So here, if I consider this and the correlations to be 0, but the same marginal distributions, as in like the same variances, then what would the asymptotics look like?
So you get the first, right? So
the second term,
yeah, as usual, you get the first. Okay, yeah, of course. I mean, the leading order asymptotics you can just get by essentially union bound. I mean, at least the upper bound. And if you do in the IAD case, of course, you get okay. well, certainly for branching random walk, you get the, okay.
Right, but for this one, branching random walk, for example, there's a difference in 3 and 1, right?
Yeah, so I mean, you can, maybe, okay. So I'm not sure that I'm answering the right question, but the leading order asymptoticity you can certainly get just by first moment. The trick is, of course, to get the second order term correct. And yeah.
Okay, so let's thank the speaker again. And for the next talk, we'll need some time for the setting up.